Guys, welcome back. At this session, what we are going to do is that we are just going to run and execute Stan program that we have. But before that, on the previous tutorial for the generated quantities, I just put the normal there. But remember that for the generated quantities, as a syntax for, I should say, for the Stan, we just go with the normal, I should say, the RNG. And that's what you should have done that, and now you see that everything is going to be fine. This is essentially the normal distribution, but this one is for the section, for the block of the generated quantities. Now that we are fine, I'm just going to go back to, I should say, to our file and execute the line. I'm going to call the model which I'm just going to have. I'm just going to call it model A because it comes with the model A in as our data that we had. I'm just going to run the file with the Stan. But before that, I make sure that the R Stan has a tick next to that. Okay. The first thing which we do, if you remember from the previous courses, I just start with the file. I'm just going to, inside the double quotation mark, put the name of the Stan file which I created before. You see that the model is called model_A_AD.Stan. And that's the thing which I'm just going to do. And you see the model is now put inside and within the double quotation mark. The second thing which I have to just put and specify is to specify the data sets which is going to be the input for our Stan model. The data here should come with as a kind of a list, and that's why I just go ahead to just put the data Stan model A. However, we have some items to just specify the number of the iterations. The number of the iterations for this one, I'm just going to go ahead with 1000. And then, if you have checked in my previous courses, you know that what do I mean by the number of the iterations and the number of the warm-up, which is going to be half of the number of the iterations. And I'm just going to specify the number of the chains as 4. And now, the explanation of all individual bits of this model is in the other course which I have. Not only we just based on the things that we have learned on the 3 previous courses, we're trying to do something incredibly interesting now. And now I have to just execute the file by pressing Ctrl Enter. You see that the file takes a couple of minutes to be run. You see that the stop sign is there. It means that the file is being executed. But depending on the complexity of the model, sometimes within 4 chains, it takes quite a bit of a time to just have your model to be executed. Then in order to save some time, I'm just going to pause the recording now. When the processing is done, I go back to continue with the rest of the tutorial for this course. Okay, now, it seems that now we are close to chain number 3, and now we have chain number 4. We are getting close towards the end of this processing. You will see that at the console. Now we have 60% sampling is done, and it's getting close to completion for, I should say, for our Stan model. Okay, now everything is done. And now you remember we had a systematic approach from now onwards, I should say towards the end, because that's the thing which we have covered before. And now the first thing that we have to just do is that we have to just check, we have a quick check for checking the convergence of the method. In order to check for the convergence, you remember we have to just use the function, the trace plot comes within our Stan package, and in order to use the trace plot, I'm just going to use the name of the model itself. I'm just going to call it model A. And I'm just going to execute the line by pressing Ctrl Enter, and we should expect to see the model being created. That's right. You see that if I zoom these plots, you see that for beta 1, beta naught, beta 1, and sigma, these 3, I should say, parameters of our interest, it seems that the convergence is done because we have, I should say, the random, I should say, sampling of 4 chains. They have been, I should say, superimposed on each other. And the rest of that is going to be for each replications that we have had. Only 10 of them has been shown, but there is more. But we are looking only to check the convergence for beta naught, beta 1, and sigma. We can also check for the convergence based on the rat statistics by checking for the model A. And if the convergence has been done, we expect that the rat statistics, it should be less than 1.1 or 1. We see that the rat statistics for all of them, it's 1.0, and 1.01 is acceptable. In case you remember, for parameter tuning, in case if you do not have the convergence, one of the methods that we covered before is that to increase the number of the iterations or reduce the step size in your, I should say, sampling. Okay, now that we have the convergence, now the thing which we do is we're just going to go to extract the posterior. And in order to extract the posterior, the thing that we do is that I'm just going to create an object, posterior. I'm just going to call that posterior for model A, because you have a couple of models. Go ahead. In order not to confuse one with the other, I'm just going to call the posterior for each model, adding the name of the model at the end of the posterior. You remember that in order to extract the posterior, I'm just going to go ahead with the function extract, which you see that that's the function which it comes within the RStan package, and that's the tool and that's the function which we are just going to use in order to browse from our posterior distribution after the convergence. I'm just going to go ahead, press Ctrl Enter, and execute the line, and the object is created there as posterior model A. We have a large list. However, if you are only interested to extract just only for one parameters, let me just first of all open that thing which we have. You see that the objects that we have beta naught, beta 1, sigma, the replicated ones, and the log posterior. And for each one, the length is going to be 2000, because you remember that we had the iterations of 1000. We have to subtract 500 warm-up from it, then multiply that to 4, because we had 4 chains, and that's why we have 2000, the length of each, I should say, estimates that we have for the beta naught. For beta naught, we have 2000 estimates, and these values have been estimated also for beta 1 and also sigma. Then we have, for each parameters of our interest, we have 2000 estimates. But which one do we have to choose? That's the thing which we are just going to talk about that, and that's the thing which we have extensively talked about that. However, if you're only interested to extract only one parameter, you can specify that by the parse method. For example, you call that beta naught. And if I execute the line, and now if I open the object which I have, you see that the posterior has been drawn only as 2000 estimates for the intercepts, which is going to be the beta naught. I'm not going to talk about that more, because these are the details that we have covered that in our previous courses. Now that we have, I should say, our posterior, the thing that we are just going to do is that to answer the question that we asked before, what is going to be the intercepts of our model? Because if you remember, in the discussion that we had, we said that what is going to be the normalized whole brain volume at the age of 60, and that was the interpretation of our, for example, of our intercepts. In order to do that, I'm just going to create an object, and I'm just going to call that B naught. Then it's going to be what? It's going to be the posterior that we have extracted, and you see that we had that extract model there. I'm just going to write the posterior model A. I'm going to get an attribute for it. And however, let me execute the line again, because we have all the 4 objects. And now I'm just going to take an attribute from it, which is going to be the beta naught. However, we have, if you remember, for this, if I execute that, you see that if it's going to be executed, we have 2000 objects. You see, if I say that B naught, I have almost 2000, I should say, estimates for the intercepts, and that's not what I'm looking for. I'm looking for, I should say, the Monte Carlo estimates that we talked about that in the previous course, and that's why I take an average and the mean of the model that we talked about that. And now you see that then for the B naught, for the intercepts, we get 0.92, which it means that essentially the person, regardless of if he is dementic or non-dementic, what stage of the Alzheimer he is in, if he is a man or woman, or what is the social economic status, and what is the level of the education, all of them, when they reach at the age of 60, their normalized whole brain volume, it should be 0.922, which it seems a little bit odd, not something that we can just readily accept that. But as I said, we are looking for a fixed effect model that no, I should say, measure, no parameter changes across different observation. However, what is the slope? And by the slope, if I call that B1, I mean the rate that this normalized or the brain volume is gonna just decrease. And the brain atrophy, essentially what do I mean is that the brain atrophy after the age of 60 is gonna be accelerated. And now I'm just looking at the rate of change for the brain atrophy. In order to do that, I'm just gonna go ahead with the posterior model A, take the attribute for beta 1, the parameters of our interest, and you see that if you just go ahead with the B1, you get 2,000 estimates for the slope. Now that's what we do, looking into, I should say, the Monte Carlo estimates, which that we talked about that before, taking the average of those 2,000, and we get that, okay, that's gonna be the level of, I should say, the level of the slope. You see that the slope is -1, which it means that in our model, if you remember, if I just go back to page number 1 of our model that we had, you remember in the page 1, we said that we may have a scenario as an alternative hypothesis that there is one more page, that maybe after the age of 60, the brain volume increases. And now you see that by this model that we had, by getting a negative slope, we see that, okay, this one is not going to be valid. The brain volume is not going to change, even though if we had no information about that from the scientific literature. By the model that we had, at least confidently, we can say that the brain volume is going to decrease because we have a negative slope for that. Then now you see that in your model so far, what we did was that we just used the Bayesian model to extract the value for, I should say, for the intercepts and the slope for our model. Then the other thing which I'm just going to do for the final part of our model, I'm just going to plot the model which I had. I'm just going to plot model A. And by plotting the model A, you will see that, for example, for beta naught and beta 1, we get the value and also the credible intervals, which is going to be first for the 80 and the 95% of that thing. Because the value of the beta 1 is too small, the credible intervals 80 and 95% is not distinctly seen. But for example, for this one, you see that the thicker one is the 80% credible interval, the dot is the mean value which we got, and the less thicker line here, it's the 95% credible interval. That you can also get the credible intervals as you wish. I'm going to also just show that how to get the credible intervals. We can just use a print function for the model A, and we see that, okay, in case if we are also looking into the credible intervals, we can get that also from here. You see that, for example, for beta naught, we have the value, the mean, which we extracted from the posterior, and also you see that, for example, the 95% credible interval comes from these two ranges, from here and also to here. You do not see that because it comes more, I should say, 0 in forward of beta 1. You do not see the full value of the beta 1 that we extracted. Okay, I think at this stage it's good to stop here before we just come for the next tutorial in order to visually plot the regression line for the data sets that we just made an inference about that using the Bayesian analysis. Okay, when we come back at the next tutorial, we are just going to incorporate some visualization and show the uncertainty around the regression line that we had to show that what is the slope and the intercepts of the brain atrophy after the age of 60 using the Bayesian analysis. Okay, then I see you at the next tutorial.